So just before we kick off, just a couple of words about me. I'm a PhD candidate at Tel-Aviv University and also a research intern at Google Research in Israel. So let's start off with a bit of a motivation, right? So we all know explainability is really important for things like reliability, accountability, and so on. But then when we train models, we're usually interested in the bottom line, right? The accuracy. What's the accuracy? What's the robustness? And then explainability is usually a field of research that doesn't naturally go along with considerations like robustness or accuracy. So what I'm going to try to do in this talk is I'm going to try to convince you that explainability is really interesting for accuracy and for robustness as well. So let's take a look at some of the topics that we're going to talk about in this talk. So obviously, all of my research revolves around attention and using attention as an explanation. And I say obviously because today, almost every model that is published has to do with attention somehow. So whether it's image classification or image generation, everything seems to revolve around attention. So in the first part of this talk, I'm going to talk about how we can use attention as a natural way of explaining the model. And then I'm going to talk about how we can leverage those explanations based on attention to improve accuracy and robustness. So we're going to talk about two ways to use attention to improve accuracy. So the first one is going to be for image classifiers for vision transformers. And then the second one is going to be for text-to-image diffusion models, how we can use attention as an explanation and leverage that to improve the images generated by diffusion models, such as stable diffusion, okay? So as I said, the first thing we're going to do is we're going to try to explain how to use attention as an explanation. So the first thing we'll need to do is kind of understand what attention is, right? So attention is a great mechanism. The purpose of attention initially is to create contextualized representations. And let's understand what that means. So for example, we have this sentence and the cute image of the cat with the phrase, the cat sat on the mat. And then the word the is quite meaningless without context, right? It has to have some form of context with it. So the purpose of the attention mechanism is kind of to create contextualized representations for each one of the tokens in the input. So we're going to create a contextualized representation for the, cat, sat, and so on. So for each word in the sentence, we would like to create a representation that takes into account the context that relates to it from the sentence. So for example, here, since the first the refers to the cat, we would expect some information from the cat to be incorporated into the representation of the word the. And then for the second occurrence of the, we would expect information from the word mat to be incorporated into the word the. So basically, this mechanism, all it does is create contextualized representations for each one of the tokens in the input in a way that considers all the context from all the directions, right? Both from left and from right. If you're familiar with NLP, then you know some of the previous models, such as LSTMs and RNNs, didn't necessarily do that. So at the heart of the attention mechanism, at least from my point of view, is the attention matrix. So in order to create those contextualized representations, we need a score for each one of the tokens, a kind of a relevance score. So this is done via calculating this attention matrix. So this attention matrix is basically a squared matrix if you're considering self-attention, right? So for each one of the tokens in the input, the, cat, sat, on, the attention matrix calculates scores, relevant scores, for each one of the other tokens. So let's observe the first row of the attention matrix. It corresponds to the token the in the sentence. These attention scores indicate how much each one of the other tokens is relevant to the token the, right? And since we're using softmax, everything sums to 1 here. So as you can see, for the word the attention values that we would expect here would assign a very high attention to the word cat, and then all the other tokens will get a relatively low attention score. So these attention scores will determine how much information will be transferred from each one of the tokens to the token the. So since cat gets a very high attention score, a lot of information is going to be transferred from the token cat to the token the. So why are we talking about all this, right? In the context of explainability, we know that the attention mechanism, usually for classification, appends an additional token called the classification token, okay? And this classification token is not a token that indicates actual information, right? It's not a word in the sentence. It's an additional token. And this token is going to get information or contextualization from the other tokens during the attention mechanism. And after we're done with the contextualization, the classification token is going to be the only one making the prediction, right? It's going to be the only token that influences the output. So then we can look at these attention values for the classification token and essentially interpret them as explanations, right? So if your attention value with regards to the classification token is high, then you're essentially directly affecting the classification more. So we can say that these attention values are actually relevance values, where tokens that get high attention value with regard to the classification token are very important for the prediction, because then the classification token is based on their information directly. And then tokens that get a very low attention score with regards to the classification token do not matter for the prediction. So we can just interpret these attention values as an explanation. So obviously we've been talking about NLP so far, right? Sentences like that cat sat on the mat, but this is a computer vision seminar. So we're interested in how to use attention in vision. So the way that we're using attention in vision is really very simple and intuitive. We take our input image, and this is the vision transformer, by the way. We take the input image, we split it into patches, okay? Usually patches with the same shape, 16 by 16, 36 by 36, and so on. And then we create a sequence of patches. So we can think of these patches as like words, right, in the sentence that we had. So previously we had that cat sat on the mat, and now we have the first patch in the image, the second patch in the image, and so forth. We use a linear projection to flatten these patches into a one-dimensional representation. And then everything stays the same as we saw before. So the attention mechanism creates contextualized representations between each one of the patches. And we have that classification token, which is the global token that is used to make the prediction. You can see it here. It's token number 0. And then we can get a relevance values for each one of the patches in the image according to this attention value of the classification token, as we said before. So we get a value, a relevance value for each one of the patches in the image, and then we can kind of draw a heat map where the relevant patches are red and the irrelevant patches are blue, but we'll see that in a few minutes. Okay, so now that we've kind of hopefully aligned on how to use attention as an explanation, and we're kind of clear on why attention can be used as a natural way of explaining things, let's discuss how to use explainability as a training signal, right? So now we have this attention mechanism where as kind of a built-in part of the mechanism, we get explanations, for free. We didn't really have to do anything very complicated for that. Now we have explanations for each one of the predictions by the model, meaning the model predicted that this is an apple. I can kind of tell which pixels in the image determine the prediction. So now that we have this prediction that stems from the inner workings of the model, right? Can we maybe use that to formulate a loss directly on the explanation? So basically, when we're trying to teach something to someone, we don't just say, this is an image of an apple and that's it, right? You kind of explain an apple is a round object and it's green or red or yellow and so on. So when we train models, we don't get to do that. But then if we look at the explanation as kind of like an additional training signal or an additional signal that we can tune or apply a loss to, then we can actually, if we buy into the premise, right, that this is the reason that the model made the prediction, we can kind of modify the way the model thinks or the reasoning of the model in a pretty intuitive way, right? The model gives us an explanation, and then we formulate a loss saying, no, that explanation is not really accurate. Let's fix the explanation. Let's fix the logic of the model. So that's actually what we're doing in the first work that I'm going to present now for image classification. So image classification is a really, really simplified task, as I said before. So the model only gets a very, very lean signal of seeing an image and then being able to classify it to one of the classes at hand. But then we don't really require that much knowledge from the model, right? All the model needs to do is get an input image and then output a prediction. We don't have any idea on what logic the model uses. So these models actually pretty, justifiably so, learn shortcuts. And maybe the most common shortcut is a background shortcut, right? So if we know that all our data or most of our data contains cows co-occurring with grass in the background, then it makes a lot of sense for the model to kind of learn that a cow is just the green grass in the background, right? Because that's what the model saw. We never actually told the model, here's the cow, and a cow is an object with 4 legs, and it has a black and white fur and anything like that. So the model can learn anything that helps it to make the prediction. So it relies heavily on shortcuts. And then we found that even vision transformers, which are considered to be relatively robust models, suffer from these biases. So the first one is obviously a background bias. And as you can see here, these models, even when you take relatively large models, not just base models, they tend to classify the image with a very high confidence of 100% or 99% or 91% based only on the background pixels. So here, for example, you see the heat map for chestnut extracted from the attention maps as we discussed before. And you can see that the heat map only focuses on the background. So it's really not even looking at the chestnut to make the prediction. And then another salient issue that we noticed is a sparse consideration of the foreground pixels. So for example, here we can see from the heat map that this is classified as zebra with a confidence of almost 100% based on only 2 or 3 pixels in the image. So really not nice behavior. So the idea would be, let's take these explanation maps and force them to be more healthy, or in other words, let's force the model to make the prediction based on the right reasons. So we have this original heat map here, and let's apply a loss on this heat map because it stems from the attention values, from the inner workings of the model. So we can easily manipulate that. It's a loss term dependent on stuff that comes from the network, right? So it's a natural loss term, just as any other loss term that we would add. So we're adding a loss term to force the prediction or force this heat map to be based on the foreground pixels, meaning the stork here instead of the lake and background pixels. So this is actually the loss term that we're applying, but then at this time I was working at the university, so we have a very obvious limitation. These are huge models and I don't have the capacity to train them from scratch, obviously. So what we did was we took a very, very short fine-tuning process, right? We're only using half the classes from ImageNet, and the reason that we're using only half the classes is to show generalization, right? So I'm using half the classes to teach the model to look at the foreground instead of the background, and then the other half classes can be kind of reserved as a validation set or a test set to make sure that the model really learns to generalize this healthy behavior of looking at the foreground versus the background. So during a short fine-tuning process, we're taking 3 labeled examples, okay? So 3 examples of ground truth explanations. So these ground truth examples will contain a binary mask of 1s in the foreground and 0s in the background. So we're only taking 3 examples per class for half the classes, and then we're fine-tuning the model such that we demand that the explainability loss on the foreground is high, and then the explainability loss, explainability values on the background are low. So these are the actual 2 loss terms that we're using, really natural, really simple. The first one is a background loss, requiring that the segmentation map on the background will be close to 0, that the relevance values on the background will be close to 0. And then the foreground loss encourages the model that the relevance values on the foreground, which is S and not S bar, will be close to 1. So essentially what we're trying to do is we're trying to teach the model, here is the object. Please focus on the object when making the prediction. And here are some results. So as you can see, we evaluated the accuracy on the ImageNet data set, but then also a lot of shifted distributions. Very famous data sets such as ImageNet A, ImageNet R, ImageNet Sketch, which are all shifted distributions from ImageNet. So these are the same classes, right, as ImageNet, but data sets that were collected a bit differently. And as you can see, for the ImageNet data set itself, there's a slight decrease in performance, both in top 1 and in top 5 accuracy. And that's kind of understandable because we took away from the model some of those shortcuts that it needed in order to make that overfit or that overfitted prediction. But then for the shifted distributions, such as ImageNet A, ImageNet R, and the SI score datasets, we can see a very, very high increase in accuracy. And that is, by the way, true for the training classes, the classes that we use for the fine-tuning, and then also for the non-training classes, which is interesting because it shows the ability of the model to generalize this healthy behavior, right? The behavior of looking at the foreground instead of the background. So really high decrease in accuracy, both in top 1 and both in top 5. And when observing some visual results, these are results obtained on the ImageNet dataset itself. So you can see that even when the model retains the same prediction that it had, for example, here the model predicted snowplow and the prediction didn't change after the fine-tuning process, the explainability maps actually make a lot more sense, because before they were focused on the background, on the snow, right? I'm not sure you can see that because it's white on a white background. And then after, the prediction is still a snowplow, but it is based on the right reasons, meaning on the foreground and the actual snowplow itself. Here you can see an example of a corrected prediction. So originally the model predicted that this puppet is a can opener, right? Based on just the eye and a very sparse consideration of maybe just the eye and the ear looking like somewhat of a can opener. And then after we encouraged the model to look at the entire foreground, right, we had that loss where the foreground pixels should obtain a high attention value. Then after fixing the relevancy maps, we can see that the model fixes its prediction without us even having to, we didn't fine tune the model to change its prediction. We just fine-tuned it to look at the right parts of the image. So this is a cool part of this work, to see that the model can actually correct its own prediction when you just tell it to look at the right places in the image, right? We didn't do anything else. We didn't use any additional training data. And then we observed that also for incorrect predictions, meaning predictions that were originally correct and then were incorrect after our fine-tuning process, the predictions actually kind of make sense, because this was classified as a tripod before a fine-tuning process, and then a strawberry after the fine-tuning process. But then we can actually see that there's a tripod and a strawberry in the image. So I wouldn't consider that to be that huge of a mistake. And here's an example of the results on shifted distributions, right? So not the ImageNet dataset, but other datasets that contain the same classes, but slightly different. So this is ImageNet A, and as you can see, before the correction, the model predicts that this is a garbage truck just because the forklift is, surrounded by garbage. So after we fix the explainability map, the model kind of fixes its own prediction, as I said before. Really cool. And here's another example of a teddy bear, which was classified as a ping pong ball just because of the angle of the footage, right? Usually the model gets footage that was filmed from the straightforward angle, and this is from above. So it actually affected the prediction of the model, and then after fine-tuning the explainability maps, the prediction is fixed. So this is actually the first work that I'm going to present, and then I see that we have some questions. Before I switch off to the next work, I'll take the questions. Is the attention matrix specific to one self-attention head, or is it aggregated? Oh, that's a great question. So we have several attention heads, right? Each attention head calculates its own attention matrix. And then I kind of skipped this part, but there's actually an algorithm that we developed in order to kind of translate those attention heads into a coherent explanation. So I do have some talks, going over that, but I don't have time to go through that in this talk. But usually it depends on the case, but usually you do some kind of a smart averaging across the attention heads to obtain one attention head. In vision transformers, is the attention score QKV as well for patch initialized for some unsupervised data? I'm not sure I understood that question. Usually it is trained during the training process of the model. So if the model was trained on supervised data, then it is trained on actual data. But then if the model is trained in an unsupervised manner, then it is trained, it's just trained during the training process of the model. So I'm not really sure I got that question and answered it correctly. If I didn't, feel free to just email me or reach out after the talk. Okay, so moving on to attend and excite. And then I'm actually pretty excited about presenting this work because it's one of the first times that I get to present it. And this work is actually on using attention and attention as explanation to improve text-to-image diffusion models. So we talked about image classifiers, and usually explainability is kind of considered to be limited to classifiers, quote, quote, right? And this is where we get to present the power of using attention and attention as explanation to improve text-to-image diffusion models. So pretty exciting work. I hope you like it too. So again, let's start with the motivation. So text-to-image models are really kind of mind-blowing and amazing. So these are all examples from Twitter, right? Of images generated from text-to-image models using pretty wild prompts, such as Darth Vader riding a bike in a forest, and then a unicorn in a wildflower meadow or something like that, or a teddy bear walking in space, or a lizard doing experiments in a lab. So these models seem to be very, very expressive and rich and be able to, kind of faithfully generate images that correspond to very, very complex prompts. But then here's a surprising thing. We tried to generate an image of a cat and a dog, and that didn't really work. So even the most basic composition of two different subjects in the same prompt didn't work. So as amazing as these models are in generating really high quality images for crazy prompts, they kind of fail miserably when it comes to putting two subjects in the same scene. And it could be, the simplest subjects as a cat and a dog. So this is really surprising. And we're trying to understand why this is happening. And after we understand why this is happening, maybe hopefully try to fix that. Okay, is it an expressiveness issue where the model can simply not generate two subjects in the same scene? Or is it an issue of neglect where the model kind of ignores some parts of the prompt? And this is what we're going to focus on during the rest of the talk. So the first thing we probably need to do is understand how the model works, right? How that magic happens of translating text into image. So specifically, this work is on stable diffusion, and stable diffusion is a type of a latent diffusion model. And what does that mean? It means that instead of operating on the original image space, which is both time and space consuming, latent diffusion models operate on a latent dimension. So the entire diffusion process is happening on a latent representation of the image instead of the original image itself, and that is for efficiency purposes. So this is an outline of how the model looks from the original latent diffusion models paper. So initially we start with an input image, right? We want to teach the model to output or clean the same image given the text. So the image X is mapped by an autoencoder into a latent space. And as you can see, the entire diffusion process happens on the latent space instead of the original image space. So after we map the image X into the latent dimension, this is the forward process. And then the forward process takes our input latent and iteratively, in a long process, adds noise to it gradually at each iteration. And then I hope you're already familiar with this, so I'm kind of going through it a bit quickly, but I hope I'm not giving you any news here. And this is the denoising process, where we take a pure noise latent, ZT, and then gradually denoise it back into a clean latent Z that we can then introduce to the decoder from the autoencoder to get our original image. So the forward process is not really interesting other than for the training process. And then the backward process is where the magic really happens. We take a random latent ZT and then gradually denoise it until we get a clean latent Z. We introduce it to the decoder from the autoencoder, which gives us from the latent an image, okay? And then as you can see, at each denoising step here, we have the queries, the keys, and the values, which are already familiar to us from the attention mechanism. So in addition to actually cleaning the image, we get additional information from an outside source. As you can see here, it's the text when we're talking about text-to-image diffusion models. So the text is introduced here in the attention mechanism during the denoising process. So then let's take a deeper look into this denoising process, into this DDPM process, to kind of understand how text conditioning is performed. So as you can see here, at each denoising step, we get a noisy latent ZT, and the network, the unit, is actually tasked with outputting a slightly less noisy latent ZT minus 1. And we kind of need to give it a hint, okay, on how to do that, because that's kind of a complex task. So in text-to-image diffusion models, we get information from a text prompt. So this text prompt is being introduced to the unit as kind of a hint on how we need to clean ZT in order to get ZT minus 1. So the model needs to clean the latent such that the image will correspond to the text that is inserted at each denoising step. And as you can see here, the prompt is aligned with a crown, but then Stable Diffusion generates a lion, but neglects the crown, as we said in the beginning of the talk. So let's take a look at how the text conditioning is actually done, right, inside the unit. So we said it's done via cross-attention mechanism. So the cross-attention mechanism, as we saw before, takes two inputs, the queries and the keys. And then the queries are representing the image latent, the actual image features, right? And the keys represent the text embedding. So this attention matrix that we saw for the previous talk also exists here. And this attention matrix will create a row for each one of the patches in the image. And for each one of the patches in the image, we're going to have an attention value for each one of the text tokens, okay? So essentially, this attention matrix actually creates a representation of which text is generated in which patch of the image. So the first row is going to correspond to the first patch. And then for the first patch, we're going to have scores for each one of the text tokens, indicating whether the text token is generated in the first patch. So now that we know what this attention matrix represents, we can take each one of the columns, and then each one of the columns corresponds to a single token in the text, right, as we said before. So we can consider each one of these columns to be kind of like a visual map of the patches in the image, where the high attention values indicate that the token is generated in that patch, and the low attention values indicate that the token is not generated in that patch. So then this is not new, right? This was done in prompt to prompt and every paper using attention for text-to-image models. So this shouldn't be anything new. So we can reshape each one of the columns to be in the shape of the image and then visualize where in the image the token is generated. So you can see the attention map visualization here for the prompt that we saw before, a lion with a crown. So you can see that the lion, the patches of the lion, kind of correspond to where the lion appeared in the image, right? So the attention values kind of give us a hint of where the token is generated in the image. So you can see that the lion is here in the middle of the image. But then for the crown, we can see that no patch in the image got a high attention value for the word crown, meaning no patch in the image actually generates a crown, right? So this is where the problem stems from. No patch in the image actually bothered to generate the crown or actually bothered to pay attention to the crown or consider the crown. And this leads to a crown not being generated in the resulting image. So we actually pinpoint the origin of the problem. Low attention equals no generation. So we can kind of look at the attention values for each one of the tokens and understand from that whether or not the token is manifested in the resulting image. And then now that we understand what the problem is, we need to formulate some kind of a way around it. So the idea of what we're doing is generative semantic nursing. And generative semantic nursing is really a complex way of just saying, let's steer the model, as we did before, towards having a healthier attention map, right? So we want the crown to have a high attention value somewhere. Let's formulate a loss to encourage the model to give the crown a high attention value somewhere in the image. And once we do that, you can see here on the bottom that the model on its own learns to assign patches for the crown and then generate the crown in a way that is natural in the scene. So generative semantic nursing is based on shifting the latent ZT that is introduced at each denoising step. So basically, why shift the latent ZT? Because as we saw before, ZT represents the queries matrix in the attention mechanism. So if we shift ZT according to a loss term that we're going to formulate, it actually means that we're modifying the queries matrix in the attention mechanism. So basically, the intuition would be, let's shift the latent ZT such that the queries matrix will change, such that we encourage the model to attend to the crown, which is currently neglected. So the only thing left to do is to define the shifting criteria, right? How do we know how to shift ZT, and what is the loss term that we're formulating here? So the loss term is going to be very... Oh, sorry, Siri thought I was talking to it. Sorry about that. So the loss term is going to be very much based on the intuition that we just indicated before. So we're going to take a look at the maximal patch, the patch with the maximal attention value. And as you can see, we can do that for each one of the tokens. So for the lion, we have a patch in the image with a very high attention value for the token lion. But then for the crown, even the maximal attention patch has a very low attention value. So the loss term that we're going to formulate is going to address that directly. So for each one of the tokens in the input, the loss term is going to reflect what is the highest attention value that the token got across the entire image. So the lion got a very high attention value in some of the patches, so this loss is going to be very low. But then for the crown, all the patches got a very low attention value, and then this loss is going to be very high. So our overall loss is going to be, consider the maximal loss considering all the tokens that we're interested in, okay? So in this case, we're interested in lion and crown, but then you can configure your tokens of interest given the input prompt. And then the loss is the maximal loss across all the tokens of interest. So we update ZT, the latent, in a gradual gradient descent process where we just shift the latent according to the gradient of the loss. So really a simple process, and it's very intuitive, I think, at least, given the intuition that we gave before. So did we solve the problem? Did we get the model to generate the entire object? We observe that sometimes the attention maps can kind of collapse to a single patch in the image. So for example, here we took a rabbit with a crown, and we kind of tried to enforce that the crown is going to be generated somewhere in the image, right? That the attention value is going to be high for some patch in the image. But then as you can see, it's not really a crown that is generated here, but just some single patch in the image got a very high attention value for a crown. And the model kind of generated what looks like a beginning of a crown and not exactly a crown. And this is because our loss formulation considered only the maximal patch, right? So it's enough that there is some patch in the image that considers the token heavily, and it doesn't really matter if, you know, the neighboring patches don't consider the token at all. So it's kind of like an edge case, but let's try to see how we can solve it. So we solve it using Gaussian smoothing. So basically what happened here was that we had this single patch here that got a high attention value, but then all the neighboring patches got a very low attention value. So what we would want to do is we would want to force that if a patch gets a high attention value, then the neighboring patches should get at least attention values that are not zero, right? So what we do is we apply a Gaussian filter. And this Gaussian filter can be thought of as kind of like a blurring map, right? So instead of just having each patch in the image focus on itself and be independent of its neighbors, then after the smoothing effect, you can see that each patch in the image is kind of influenced by its neighbors. So for example, here, the maximal patch that was once before, you know, looking very strong and very sharp, it is now kind of blurred out due to the effect of its neighbors. So basically, every patch is going to be a linear combination of the patch itself and then also its neighbors. So instead of applying the loss term directly on the attention maps, we apply them on the smoothed attention maps after applying Gaussian smoothing. And then the loss is the maximal loss as done before, and we update the latent according to the gradient of the loss. So this is actually the result of a rabbit with a crown after applying Gaussian smoothing. So now this wouldn't fly because the attention map after the smoothing would indicate that this attention value is kind of decreased by its neighbors, which have a 0 attention value. And after applying Gaussian smoothing, you can see that the actual crown is generated entirely for the rabbit. So let's take a look at the entire process that we just described because it was a long one. So we had a DDPM process where the model was tasked with given noisy latent, producing a slightly less noisy latent. And we gave the text as kind of a hint to the model on how to denoise this latent. And then we took a look at the cross-attention mechanism, which is the mechanism that actually incorporates the text into the denoising process. And we saw that we can extract a spatial attention map for each one of the tokens. And this spatial attention map indicated whether the token is generated in the image or not. So then we took these attention maps and formulated a loss directly on the attention to require that in some patch in the image, no matter which patch, right? The model can select which patch will have the high attention, that in some patch in the image, the model will consider each one of the tokens, lion and crown. And then we updated the input latent ZT such that the latent is encouraged to consider all the inputs in the text. So you're probably wondering what happens if you have more than 2 tokens to enforce, right? Because we only took the loss according to the maximal or the most neglected token. So what happens if you have 2 or 3 or 5 neglected tokens in the sentence? So this is why we introduced iterative refinement. So basically, iterative refinement also means, okay, so we shifted the latent slightly, but what if that wasn't enough? You know, in the first parts, in the first denoising steps of the process, the locations of these subjects is really determined. So if you don't really enforce the high attention in the first denoising steps, then the object will not appear, right? The last denoising steps do not really have an effect on that. So the idea is to keep updating the latent until a certain threshold of attention is obtained for all the tokens of interest. So basically what we're going to do is, giving our denoising step, right? We're going to compute the loss for each one of the tokens that we're interested in. We're going to compute the shifted latent, okay? So we're going to shift the latent according to the loss, and then compute the loss again. And then we're going to ask, is the loss low enough? Meaning, did we obtain the attention threshold for each one of the tokens of interest? If the loss is low enough, we can continue on to the next denoising step. But if not, we're going to repeat this process iteratively. So assume you have 2 neglected tokens, right? Say both lion and crown were neglected. Then the attention value for the highest attention value for lion will be, say, 0.4, and for crown will be, say, 0.3. So the first step is going to compute the loss on the crown, and then assume we fixed the crown, and now the crown has a high attention value of 1. Now the lion will be the dominating part of the loss, and in the next iteration, the lion will be fixed, right? So this iterative refinement process ensures that all the neglected subjects get their claim to fame with the loss function. So this is done repeatedly until we reach a certain attention threshold for each one of the subjects in the input. And now you have to be kind of careful about performing iterative refinement because you may end up getting out of distribution, right? You may end up pushing the latent too far out of the distribution of the original latents that the model is used to get. So we do that gradually. At step 0, at denoising step 0, we demand a threshold of attention of 0.05, okay, so not that high. At step 5 of the denoising, we demand an attention value of 0.2, and at step 20, we demand an attention value of 0.8, just to make sure we do that gradually and not push the latents too far out of the distribution that the model has learned. So now let's take a look quickly at some results. So this is a cat and a dog, as we saw before. So this is stable diffusion. So it either generates 2 cats or kind of a weird mash of a cat and maybe a dog's body. And then we also compared against baselines such as composable diffusion and structured diffusion. And as you can see, they kind of fall short in generating both subjects in the image. But then when using attend and excite, both subjects are generated, which is a first good sign. But then another thing I like about these images is that they are actually diverse, right? We have multiple breeds of dogs and cats in multiple angles and shapes. And this is just because the loss term formulation didn't require anything specific from the model, right? It was free to determine the locations of each one of the subjects without us intervening. We just demanded that there is some patch in the image where the attention value is high. So here's another neat thing that we noticed. There's an additional problem to text-to-image models where they don't adhere to the attributes that were attached to each one of the subjects. So for example, here we want a red bench and a yellow clock. And you can see that some of these benches are yellow instead of being red. And when a clock is generated, it is red instead of yellow, okay? So the model does not really know how to bind the attributes to the subjects. And we can see that by using attend and excite, we solve both issues. So all the subjects are generated in the image, and then kind of as a neat side effect of using attend and excite, the correct attributes are also binded to their subjects. So the clock is yellow and the bench is red, which is kind of neat. It also works on, as we said before, complex examples with multiple subjects. So this is a playful kitten chasing a butterfly in a wildflower meadow. And as you can see, before applying attend and excite, which is our method, the kitten was chasing itself in the meadow. And then after applying our method, the butterfly is generated, but then the images also kind of correspond nicely to the prompt because the kitten kind of seems to chase the butterfly around the meadow, which is a nice result. And here's another complex prompt, a grizzly bear catching a salmon in a crystal clear river surrounded by a forest. So as you can see here, the salmon was not generated before, and after it's generated, then the bear also seems to catch the salmon, which is a nice added bonus. So there are a lot of problems that we didn't solve. First of all, there are prompts that are surprisingly just, the model just fails to generate them. So here's a surprising one, a dog and a bear. And this is even after applying attend and excite. So you can see that sometimes you get kind of dogs and bears, and it does work for 5% of the cases or so. But then these are prompts that the model just simply miserably fails with. And attend and excite is usually really good at taking the model from the 20% success to the 70% success and even the 100% success rate. But then when the model completely fails because it's not expressive enough to generate both subjects in the image, then attend and excite cannot help, unfortunately. And then another limitation is that when you have a prompt that is kind of surreal, such as an elephant with a sombrero, you can see that attend and excite usually generates images that are less realistic. So it kind of adheres to the prompt, but then in order to adhere to the prompt, the images are less realistic than we would expect them. And then we also didn't deal with another major issue of text-to-image models, which is object relations and compositions. So writing on, behind, on top of, to the right of, bigger, smaller, and so on. So these are all very complex issues that I think would require a bit, more interference than just manipulating the attention maps, because we didn't actually do anything or introduce any new training data. So this is going to be a bit tougher to do. So let's sum up everything. So our method is applied at inference time, right? It wasn't applied during training. We took the latent and then we shifted it according to the criterion, and it didn't require any additional training data, which is kind of neat, but then also limits us if we want to solve really complex issues such as compositions. It draws some similarity to classifier free guidance because it allows you to kind of select how much dependence you want to have on the input text, right? If you apply attend and excite, then you know that necessarily you demand that the image kind of corresponds to the text better. And the idea of generative semantic nursing is potentially generic, right? We used it to kind of manipulate the attention maps, but then you can apply the same logic of shifting the latent and use any loss term that you would choose, not necessarily even on the attention maps. So the idea of kind of gradually shifting the latent in order to get the generation to adhere to some objective that you wish to you wish to enforce is potentially generic. So you don't have to do that according to the attention maps. You can do that according to any criterion that you choose in order to enforce other things on the generation. So maybe you can enforce semantic things as adhering to a segmentation map or anything else that you can think of. So the idea is actually generic. And here's another neat thing about this work. This was also done at the university. So we didn't have the resources, obviously, to train Stable Diffusion. Didn't have the resources to train the vision transformer. But then we did all these things using really low resources because we knew how to kind of manipulate the inner workings of the model. And this is, I think, the main takeaway from this talk. If you understand how the model works, you can kind of manipulate its logic based on the explanation. So you get your explanation, and then you formulate a very intuitive loss term on what you want the explanation to be. For example, you want the explanation to be based on the foreground, or here you want the explanation to contain a patch for each one of the subjects. And then you manipulate the model to adhere to your criterion that you defined very intuitively. And the model actually corrects itself, which is kind of an amazing thing. So understanding how the model works and explaining the model can actually help you improve the accuracy and improve the robustness across a large variety of cases. So we saw image classification and text-to-image generation. So I really hope you enjoy the talk, and I'm going to take the questions in the Q&A form right now. Could you give some intuition on how to create a differentiable loss function that can help differentiate between the foreground and the background for vision transformers? A link to your paper could be helpful. Okay, I'll add a link to my paper after the talk, right? And then an intuition on how to create a differentiable loss. In the case of using attention, it's kind of very intuitive because you can kind of formulate any loss term almost on the attention mechanism, because the attention mechanism is something that stems from the model itself. So you can think of it as kind of like a byproduct, an addition to the prediction itself. And then you can formulate any loss term that you wish on the attention mechanism. As you saw here, we can also demand that some patch in the attention, some patch in the image gets a high attention value. So you can really formulate any loss that you want on this attention mechanism, because it is a part of the internals of the model. So I hope that answers that question, Daniel. But if it doesn't, I'd be happy to answer that offline. Why do stop words have strong maps, since they might not be affecting the output? Oh, that's a great question. Thank you for this question. So these maps are actually normalized between 0 and 1, right? So let me just circle back to the attention maps for E, A, the, and so on. Yeah, so as you can see, there are patches that are strong for A, and it's just because we take the column and then normalize it between 0 and 1, such that all the values are between 0 and 1. And this is just for the visualization purpose, but then all the attention values for A are really low. They're just, some of them are lower than others. So when you normalize between 0 and 1, it kind of looks like there are high attention values, even though there aren't. So thank you so much for that question. If we change the question to a crown on a lion, will the error be the same? That's actually a very interesting question, because we do see kind of dependence on the order of the subjects in the input. So as you can see here, we had a cat and a dog, and then the cat was mostly generated. It seems to be the case for stable diffusion models, but I'm not sure it's the case generally. So if you had a crown on the lion, maybe it would give better results, but not in all cases. And it's actually an interesting question. It does happen for stable diffusion that it regards more the subjects that are in the beginning, at least from what I saw, but it's not based on actual statistics or data. So that's an interesting question. And yeah, may you please do share a real world scenario where the attention mechanism that you have explained could be useful? I mean, I think this is kind of a real world scenario where you can use the attention mechanism, right? The attention mechanism is used to condition almost anything on anything today, right? And then here's a really, really practical use case where you can use attention to kind of manipulate the model to do what you want it to do. Do you share the slides after the session? Sure. Yeah, we'll share the slides after the session. Thank you so much. And if you have additional questions, please feel free to kind of reach out via email or chat or anything after the talk. So thank you so much.